Okay, good afternoon, everyone.
Good afternoon.
Today we're gonna, so last time we reviewed the idea of a subspace, and we gave an example of subspaces, which is the null space. And to help us a little bit interact with subspaces, because they are a little bit abstract, so think always like in R3, like the subspaces are lined through the origin. So start imagining what they are, playing through the origin, all of R3, and this will help you a little bit interact with the idea of a subspace. Now, basis of a subspace. What is a basis for a subspace? So let H be a subspace of Rn. It means this collection of vectors that have very specific properties. And V1 through Vk are vectors in H. So we have this collection and you have a bunch of vectors in it. Then we say that the vectors V1 through Vk form a basis for H if the following two conditions are satisfied. First, the vectors are linearly independent. So I have a subspace, I have a bunch of vectors in it. We say that they form a basis if those vectors are linearly independent. Second, which is a very important one, the span of the V1 through Vk is all of H. Remember, the span is all possible linear combination of V1 and Vk. Then the span equal to H, which means that every vector in H is a linear combination of V1 through Vk. So if we have a subspace and we have a bunch of vectors in it, we call them a basis if the following conditions satisfied. So they are bases. It means that everything in H is a linear combination. So everything is obtained from them. And at the same time, we want them to be linearly independent. So we don't want a lot of them. So we need the minimum number of vectors needed to span the subspace. Okay? So this is the definition. Now we're going to take a lot of examples. My first example, we're going to work on it very thoroughly, and then the rest will become easier. I'm going to take my subspace to be R2. Okay, it means all vectors with 2 entries. And the question is, let's find a basis for R2. What does it mean to find a basis for R2? So my subspace now is R2, all of it. Find a basis, it means I need vectors in R2, finitely many, that have the property. They are linearly independent, and everything in R2 is the linear combination. So who can think of a basis for R2? So that's my definition, and now we're going to take up examples. So my H is all of R2. That's my subspace. And we want a basis. So that's my example 1. Means I need vectors that span R2 and they are linearly independent. What are the easiest vectors that you can think of that have this property? Anybody? I'm going to start with, to get you going. Exactly. Suppose I take E1 to be the vector 1, 0. Vector right here. That's E1. and E2, actually I use red, and E2, the following vector. Okay, E2 is the vector 0, 1. Then those two vectors, E1, E2, they form a basis for R2. A basis for R2. And let us see what. What does it mean to form a basis? First, they have to be in R2, and they are. They have to be linearly independent, and they have to span R2. And the question is, do those two vectors have this property? So first, E1, E2, because, so they form a basis because E1, E2 are obviously linearly independent. There are two vectors, and of course they are not scalar multiple. Or if you can put them in a matrix form, definitely there is no free variable. They are linearly independent. Second, their span, it means all their linear combination. If I take every possible linear combination, I should be able to get all of R2. It means any vector in R2 is a linear combination. Now, we've seen in class that any two linearly independent vectors in R2 span R2, but in this scenario, it's very easy because if X is any vector in R2, any vector, I can write it as X1 E1 plus X2 E2. Means any vector is a linear combination of E1 and E2. So the span of those vectors is all of R2. So E1, E2 form a basis for R2 because they are linearly independent and span R2. This basis has a specific name. E1, E2 is called the standard basis for R2. It's called the standard basis for R2. Okay, so my subspace is R2. Finding a basis means find vector that covers all of R2 in the sense that the linear combination or their possible linear combination will give me every vector in R2, and at the same time, we want them to be linearly independent. Now, is this the only basis for R2? Can we think of other vectors who can form a basis for R2? So E1, E2 are basis because that's for all the condition, and they have a specific name. They are called the standard one. Now, are there other bases for R2? Can anybody think of another basis for R2? Again, my subspace is R2, and the question is, can I think of another basis? So again, my subspace is R2, and I'm going to give another basis. Can anybody think of another one? Okay, suppose I take V1 to be 1, 1. Whatever you guys are giving me, 0, 4. So let us take the first one, 1, 1. And V2, what your classmate is giving me, is minus 1, 1. Okay, and so graphically, the first vector is 1, 1. That's my first vector. That's my V1. And the other one is minus 1, 1. That's my V1 and my V2. Okay, do they form a basis? So the question is, determine if they form a basis. And do they form a basis for R2? And let us see why. Because first, V1, V2 are linearly independent. So first, we're going to check for linear independence. Okay. Obviously, they are linearly independent because they are not scalar multiple, and we're talking about only two vectors. So, or we can So V1, V2 are linearly independent because they are not scalar multiple. They are only two vectors. They are not scalar multiple. Scalar multiple. So obviously linearly independent. Or you can check the augmented matrix and ask yourself, do we have a free variable, yes or not? If you do that, you will definitely get this scenario. Okay, so no free variable, it means linearly independence. So they are two. We have to check that the span of V1, V2 is equal to R2. Is this the case? Is this correct? So you guys are giving me tons of them. There are a lot. Is the span equal R2? Is any vector in R2? So any vector. Can I write it as a combination of V1 and V2? Any vector in R2. Geometrically, we can, because geometrically, that's what we did earlier in the beginning. We can go a little bit in the direction of V1, actually like this, and then we can back up in the direction of V2, and geometrically, I can write it. Now, algebraically, because the geometry carries so much, so check that, and it means we have to check that everything in R2 is a linear combination. But we know that for two reasons. First, let's see why this is true. I'm going to give you two reasons. Suppose B is any vector in R2. B, B1, B2. Okay? Any vector in R2. And when we try to solve, suppose we solve the following system. It means we try to find a weight such that this hold. Suppose we have tried to solve that. Will this have a solution for all B? Okay, if we write the system, V1, V2, and I put my vectors V1, the one you guys gave me, and I try to ask myself, do I have weight? We know what's going to happen. This piece is going to turn into that, and this will turn into something. Now, regardless what B is, the system has a solution. There is no inconsistency. Because regardless what I put here, because I have a pivot in every row, the system is consistent. So here, since we have a pivot in every row, pivot in every row of the augmented matrix, sorry, of the coefficient matrix, the system is consistent. We have consistency. What does it mean to you? It means no matter what you put here, I will be able to find weight that will let me write B as a combination of x1 and x2. So the span is all of R2. Okay? Another way you can say it is you can refer to the invertible matrix theorem, which tells us that any two linearly independent vectors in R2 span R2. So this is another basis for R2. Their vectors are linearly independent and they span. Okay, so those are vectors that anything in R2 could be made out of them. That's really what the basis is. All right, let's take a few more examples. So there are a lot of bases. You guys gave me a lot of examples, but let me ask you now some example myself. Actually, we can have a rule which tells us the following. Any two linearly independent vectors in R2 form a basis for R2. Okay. Now let us ask you again, because I want to hammer R2, everything else will become much easier. Again, H equal R2. And suppose I give you the following vectors. 1, the one you guys gave me, like 1, -1, 1, 1. And suppose V2 is -1, 1. And V3 to be 3, 4. And the question is, determine if the collection of vectors v1, v2, v3 form a basis for R3. Sorry, for R2. Okay, what will be the situation? So now I have R2, I have 3 vectors in R2. They are in my subspace. And my question is, do they form a basis for R2? We always have to remember the criteria for a basis. Vectors form a basis if they are linearly independent, and if everything in R2 could be written as a linear combination. So now I go back to this question. Do those vectors form a basis for R2? So we have to check 2 things. First, we're going to check for linear independence. Now, are the vectors v1, v2, v3 linearly independent, yes or not? Back to you. Are they linearly independent? Okay, I'm having a yes. We're in trouble. How many vectors are there? 3 vectors. 3 vectors in R2. Could they be linearly independent? Let us remember what's the scenario. And then we remember the rule. How do we check linear independence? We have to solve. Let us check it. And then I remind you the rule. Let us check. It means we solve this equal to 0. Remember how we show linear independence. We solve this vector equation and we ask ourselves, do we have a unique or infinitely many? So if I solve this vector equation, how many solutions we're going to have? Watch carefully. Each one of them is a vector in R2. Each one of them is a vector in R2. Each one of them is vector in R2. Now, when we solve, what's going to happen? Are we going to have a unique solution, or are we going to have infinitely many solutions? I'm not going to solve just by looking at it. What's going to happen here? Infinite. So we're going to solve that. So now, if we look at the augmented matrix, okay, we definitely have a free variable because we have at most 2 leading. Means one of the variable will have to be free. I don't care which one, absolutely not. So we have a free variable. Immediately, it means the vectors are linearly dependent. Okay, so let us recall the following fact based on this remark here. Any 3 vectors in R2 are linearly dependent because when we are solving, we have to have free variable. Okay? And geometrically, if I have 3 vectors in R2, those are 3 vectors, v1, v2, v3. One of them, 2, will actually span R2. It means the third, I should be able to write it as a linear combination of the other 2. So geometric, if I have 3 vectors, if 2 of them are linearly independent, those 2 by themselves cover R2. So the third one is actually an extra. It doesn't really do much because this can be written as a linear combination. But in general, any 3 vectors in R2, not in general, a rule, any 3 vectors in R2 are linearly dependent. And that's the algebra behind it. So this means that those vectors do not form a basis. Do not form a basis. So v1, v2, v3 do not form a basis because they are linearly dependent. Do not form a basis for R2 because they do not satisfy the linear independence condition. They may span R2. It means very possible those 3 vectors, if I take all possible linear combination of them, I will get all of R2 because 2 of them will cover R2. So the third is really actually an extra. But they do span R2, absolutely. But basis require them to be linearly independent. Basis requires intuitively, we're looking for the minimum number of vectors needed to span R2. 3 vectors is too much to span R2. That's really the idea of a basis. So the linear independence is a requirement to make sure that we're having the least amount of vectors possible to cover all of R2. That's really what the linear independence play a role. So in my case, those absolutely do not form a basis. They span R2, but basis requires 2 conditions. This one is not satisfied, so we do not form a basis. Okay. Now, one more questions about, again, R2. I will, as I said, I will cover R2 very easy, clearly, and then the rest will become simpler. So again, my subspace is R2, not changing it. And I have the following vector. So let V1 to be the vector 1, 3. Okay, and the question is, determine if V1 form a basis for R2. So that's a unique vector, form a basis. So what do you think the answer is? Can one vector form a basis for R2? Yes or no? So, okay, I'm having a no for answer, absolutely no, because which condition is not satisfied immediately? Which condition is not satisfied immediately? 2 conditions are required. The span is not, no, because the span of one vector is actually a line. So if I am in R2 and I take only one vector and I take every possible linear combination of it, I just get this line. So that's the span of one vector. So this is not R2. Absolutely. So one vector do not form a basis. So I need 2. I need 2 linearly independent. Okay, one more for R2. And then I can move to R3 and other stuff. So again, my subspace is R2. And these are my vectors. I'm giving them fairly easy vectors. And do they form a basis? Okay, yes, no. Absolutely no, because just by looking at them, basis, you have to have independence. So no, because V2, of course, I gave them easy, is 2V1, so they are not linearly independent. So I don't really care about the span because already 1 is not satisfied, not linearly independent. So that's really the idea of a basis for R2, and that's going to be the idea of a basis for actually R3 and for anything else. So in R2, what's really the scenario? If you can summarize R2. So for R2, that's really the scenario we have for R2. So we have the following scenarios, the vectors you guys gave me. It was -1, 1, I forgot, and 1, 1, I imagine. Those form a basis because everything was satisfied. Equal R2. The minute I plopped in a third one, I just added a third, not a basis. Because linearly dependent, even though as you guys said, their span is everything. So I can get everything as a linear combination, but there are too many of them. And basis doesn't want a lot of them. They want the minimum number needed. So that's not basis. And then we took the other scenario, whatever, I forgot what I put, minus 1, 1, not basis because the span condition is not satisfied. So that's the picture for R2, okay? Now, R3 is the same. There is really nothing different about R3. So I'm gonna ask you several questions about R3, but we should be able to answer them very easily. So example number 5. So I'm gonna give you a bunch of vectors and we're gonna decide what, I don't know, I think it's example number 5. And so my subspace here is all of R3. So we're keeping it to in simple scenario now. And my question, determine which of those vectors form a basis. Determine which of the vectors below form a basis for R3. Right. Okay, so let us see. Suppose I give you the basic vectors, 1, 0, 0, 0, 1, 1. I always bring this up because we should know that those form a basis and they have a specific name. Okay, do those form a basis? Yes or no? Quickly, I want to answer. Yes. They are absolutely linearly independent. E1, E2, E3. First, they are linearly independent. The only way you can combine them, get the zero vector if the weight are 0. And second, they span all of R3. The span is all of R3. Any vector in R3 for this simple scenario can be written as their linear combination. And I don't need proof because any vector, I can write it as x1 E1 plus x2 E2 plus x3 E3. So they span everything is a linear combination. And this is, as before, that's called the standard basis for R3. So when we hear about the standard basis for R3, we're talking about the E1, E2, and E3 vectors. So the standard basis for R3. All right, very good. Now let us take other examples, again for R3. So let us say I take the following. The vectors 1, 2, 3, and the vector 2, 3, 1. So these are my vectors. And the question, do they form a basis? Now, back to you. Do they form a basis for R3? Okay, R3 is my subspace. So of course they are vector in R3. First, we can check for linear independence. And check for linear independence. And okay, you can check for it. Since they are only 2 vectors, they are not scalar multiple. Only 2 vectors, I can use that. They are not scalar multiple, therefore, so V2, not scalar multiple of V1. Of V1, it means they are linearly independent. But that's not enough. That's not really enough. What matters is also, we want them to cover all of R2. So all of R3, sorry. So if I take their span, those are 2 vectors. And if I have 2 vectors in R3, and if I start taking every possible linear combination of them, what do I get? This is no way I can get all of R3. Because if I take 2 vectors and I start combining them, every vector which is up here, every vector which is up here cannot be written as a linear combination because geometrically, the span of those two vectors is nothing more than the plane through the origin that contains those two vectors, through the origin that contain those three vectors. So there is no way they can do that. This is just a plane through the origin. We cannot get all of R3. All right, so C. Let's take two more examples. Suppose I take those vectors. Let me write those on a nice piece of paper. Suppose I take the following vectors. 1, 2, 3. And let us see, 2, 3, 1. And -1, 5, 0. So this is my V1, my V2, and my V3. Okay, and my question is, do they form a basis? Yes, absolutely. For the previous example, I need a third one to span R3, so they don't form a basis. The basis for R3 are vectored such that everything in R3 is their linear combination. There is no way. They have to cover all of R3. Okay, good questions. Now C, do those form a basis? I have three vectors now. Do they form a basis? I mean, do they satisfy these two conditions? Okay, I have three vectors, I have no idea. I first have to check for linear independence. There is no way out. But the minute I give you three vectors in R3, first we need to check for linear independence. If they are linearly dependent, I am done. If they are linearly, if they are linearly dependent, they don't. If they are independent, and then we look for the span. So check linear independence. It means I need to solve, so this actually helps us to remember, means I have to solve this vector equation and ask myself, am I having only the zero solution or non-zero solution? So we have to put them in an augmented matrix to solve. Remember, I'm solving for x1, x2, and x3. And we row reduce, 0, 0, 0. We row reduce, so you guys row reduce it. I won't do that now anymore. I get this, 0, 0, 0. So I'm getting the identity. So this tells me that x1 equal x2 equal x3 equal to 0. So the vectors are linearly independent. So now I have three vectors in R3, and they are linearly independent. So now is the span, do they cover all of R3? So three linearly independent vectors. Do they cover all of R3? Yes or no? Okay, so is every vector, so now we know that they are linearly independent, and now my question is that is every vector in R3 could be written as their linear combination now? And let us remember, the answer is yes. Let us remember why. Because if I take any vector in R3, any vector, can I solve? Can I solve? It means, can I find weight so that if I put on the V1 and V2 and V3, I can reach the vector B, regardless what B is? And let's see algebraically why it is true. And this also reminds us the fact. Because if I solve now, so I solve 1, 2, 3, 2, 3, 1, -1, 5, 0, and B1, B2, B3. And the question, will this have a solution, regardless what the weight are? Now, because they are linearly independent from above, when I'm going to reduce, I'm going to have that. But I don't know what does happen here. I'm going to have this, something will happen, and I'm going to have that. And this because they are linearly independent. And because there are three of them, every row is having a leading. So there is no room for inconsistency here, because I have a leading into every row of the coefficient has a leading. So it means that this scenario cannot occur because I have a leading in every row. So this is consistent. This is always a consistent system. Since the coefficient has leading in every row. So there is no room for this scenario. Every row. Okay, so in general, and this really help us to remember, in general, any three, and I've talked about that before, but now it's time to review it. Any three, and there have to be three, linearly independent vectors in R3 will span R3. It means it gives me any vector in R3. And the reason is, if there are three of them and they are linearly independent, that's the picture for the augmented. So I have to have a solution. So definitely they form a basis. Form a basis. And this will bring us to the theorem. Any three linearly independent vectors in R3 form a basis for R3. And they are linearly independent and they cover R3 because of this reasoning. So we can have this again now as a rule if you want. Any three linearly independent vectors in R3, they have to be three. Any three linearly independent, that's crucial. If they are dependent, I'm after picture vectors in R3 form a basis for R3. Okay. One last example for R3. Is the more general rule? Absolutely. Any n linearly independent vectors in Rn form a basis for Rn for the same logic that it is here. If you have four vectors in R4, this one is going to look like that. It means regardless which vector I put in here, I'm going to have a solution. No inconsistency will occur. If I have five vectors in R5, then again, the same picture will show up. All right, so my last example for R3 is simple. Suppose I have I'm going to put the same vector that I had before, 1, 2, 3, 2, 3, 1, and minus 1, 5, 0, and finally 4, 17, 18. Those are four vectors in R3. And the question, do they form a basis? Yes or no? Do those form a basis? So always linear independence. And the same reason why three vectors in R2 are linearly dependent, four vectors in R3 will be necessarily linearly dependent. And then, so now any four vectors in R3, because algebraically it fails, are linearly dependent. Because when you try to solve your system, you're going to have three equations, but you have four unknowns because you have four vectors. So this forces one of the variables to be free, causing the linear dependence. So they do not form a basis. Even if they span R3, because they do, because every vector in R3 could be written as a linear combination of those three. So they do span R3, but basis want, as I said, the minimum number of vectors needed to cover all of R3. And 4 is not the minimum number of vectors. So do not form a basis for R3. So to show that for R2, R3, R4, this is the example I'm taking. So now that they form a basis, you have basically to check first linear independence and then the span. Two things has to be satisfied. So suppose my last example, it's simple. Suppose I take those three vectors here, for example, and I'm gonna make them very trivial. 1, 2, 3, 3, 4, 5. And I'm gonna take this one to be 4, 6, 9. So those are three vectors, but do they form a basis? Do they form a basis? So not any three vectors form a basis. So first we have to check linear independence. This has to be satisfied. If it's not, it doesn't mean they form a basis. So not every time I throw three vectors at you in R3, you say yes. So if I check here linear independence, 1, 2, 3, 3, 4, 5, and if you, the way I constructed this first one to be 1 plus 3 is 4, 2 plus 4 is 6, 3 plus 5. So I really built them so that this is a combination of those two, which I'm going to stop the linear independence. So if you do that, you're going to get something along those lines. That's a free variable. Those are dependent, so not a basis. So not every time we have three vectors, we have a basis. We have to make sure that those vectors are linearly dependent. So for R3, we have the same picture. Of course, one vector is not a basis for R3 because it doesn't span it. Two vectors do not form a basis because they can't span it. Three vectors may or may not, depending if they are dependent or independent. Four vectors are out the picture because they are linearly dependent. So that's really the idea of a basis for R2 and R3. Now there is the idea of dimension of a subspace. Okay, dimension. But before I do the dimension, I want to take examples a little bit, not R2 and R3, so to clarify the picture. Suppose I tell you that. I tell you let H, so now H is not R2. H is the following vector, this following space. All the linear combination of the vector 1, 2. Okay, so now H, I'm changing. It's not R2, it's not R3 anymore. H is a subspace of R2 because this is 1, 2. H is the span. It means every possible linear combination. So H is, this is 1, this is 2. That's 1, 2. H is this one, every possible linear combination. Okay, and now I'm going to ask you a fairly simple question. Give me a basis for H. What's the basis for H? It means I want something. I mean, it's simpler than you think. I want vectors are linearly independent. And when you span them, you get all of H. So what's the most natural basis for this subspace? Exactly, the vector V1, 1, 2. That's a basis for H. Okay, so in this case, if you have your subspace is basically this line, the basis for it is just only one vector on the line, because when you span it, you get everything. And now I want to bring up the definition of a dimension of a subspace. What's the dimension? So if H is a subspace, then the dimension of H is a number, is the number of vectors, it's a number, it's the number of vectors in the basis of the subspace. So the dimension of a subspace is the number of vectors in the basis of a subspace. So now when we talk about the dimension, it means we are talking about how many vectors are in the basis. So with this in mind, for example, the dimension of R2 is how many vectors are in a basis for R2. R2, any basis will have to have two linearly independent vectors. So the dimension of R2 equal to 2. And you guys have used intuitively that the R2 is two-dimensional. But mathematically, what it means? Mathematically, the dimension of R2 is 2. It means that you need two basis vectors to cover all of R2. That's what really mean mathematically by the dimension. The dimension of R3 is equal to 3. It means a basis for R3 consists of 3 vectors. Now, if H is the span of 1, 2, so that's an example, then the dimension of my H is equal to 1. So H is a one-dimensional. Matteo, I don't understand. And you need 3 vectors for bases. I can't follow your question. Okay. In this case, the dimension of H equal to 1 because one vector is needed to cover the line. So this is my line, 1, 2. This vector is enough to give me every other vectors in H once I start stretching it and contracting it. So dimension of this H is equal to 1. So that's what the dimension of a subspace is. How many vectors are needed? How many linearly independent vectors are needed to cover the subspace we're talking about? Okay. Now, again, we try of digging a little bit into understanding subspaces. I have the following question for you. I want you to think about it a little bit. I'm telling you that let H, so it's a little bit more abstract, but it helps us understand the notion. Let H be a subspace of R4. I picked R4 on purpose. It means that H consists of vectors in R4. It means consists of vectors that have 4 entries. And H has the property that the sum of two vectors in R4 in H remain in H, and scaling a vector in H stays in H. And you're told, I'm telling you the following. You're told that the following vectors, 1, 2, 3, 4, and 4, 3, 2, 1, so that's what I'm telling you, form a basis for H. So that's what's given to us. So I have a subspace, and I'm telling you that those two vectors form a basis for H. What am I telling you? Okay, so before I ask my question, what does it tell you? What does it mean to you? So telling you that they form a basis for H tells you what? Two things. Then they are linearly independent, but I don't need them because I know that they are linearly independent. I just look at them. But more importantly, what else do they tell you? Okay, they are very good. They are contained in H. So those two vectors are in H. What else they tell you? To tell you that they form a basis. It means what else they tell us. What else they tell us? Form a basis, that's the main idea. They are telling me they are linearly independent, exactly. And that tells me that their span is all of H. And that's the crucial idea. So by telling me that they are a basis, it means they are telling me what H is. Basically, they're giving me H. It means they are telling me that they are linearly independent, of course. But more importantly, they are telling me that what H is. They are telling me that H is nothing more than the span of those two vectors. That's what's the idea. It means everything in H, they are the basis of it. Everything in H is nothing more than their linear combination. And that's really the crucial idea. So what does it mean to you that tell you that it's a basis? It means they are linearly independent, and everything in H is obtained as a linear combination. Means that's what H is. That's what it is. It's a combination of those two. So now my question is the following. My question is the vector 2 minus 1 minus 4 minus 7 in H? How can I answer this question? So I told you those vectors form a basis. Now I'm asking you, is the following vector in H? How can I answer this question? Okay. Anybody? I mean, I'm reading everything you guys are writing. No, they are independent. No? Is this vector in H? Read carefully what I wrote. Read carefully what I wrote. Telling you that those two vectors form a basis means I'm telling you that H is nothing more than the span of those two vectors. That's what H is. So, is this vector in H? Exactly, it means, can I get this vector as a linear combination of those two? Because that's what H is. Telling you it's a basis, it means everything in H is nothing more than the combination. So is this vector in H? It means is the vector. That's really what it is. It means is this vector a linear combination of the vector 1, 2, 3, 4 and 4, 3, 2, 1. That's really what it really is equivalent to say. So is it in H? It means is it a linear combination? Because telling you those are form a basis, it means they are everything. Everything in H comes from them. So now I have to ask myself. So now I have to solve the system. So now I need to solve the following system. Can I find weight that I can put on those basis vector that will give me this one? That's really now what I need to ask. So asking you, is it in H? It means, can I put something here to reach that vector? Now at this stage, this has become back a problem that we've done like a million times by now. I just have to solve correctly. And I ask myself what happens. So 1, 2, 3, 4, 4, 3, 2, 1, and 2 minus 1 minus 4 minus 7. Now I solve it. And of course, I'm not going to do that by now. And I think I did that by myself. After solving it, I use the computer to do it. And I get the following. Minus 2, 1, 0, 0. Okay, so it means that this is a consistent system. And actually, I can read the weight. So x1 is minus 2, and x2 is 1. It means that my vector 2 minus 1 minus 4 minus 7 could be written minus 2 times the first plus the other one. So it means the vector is in H. Is in H. Okay, so the idea is that when they give you a basis, which is something, you know, eventually in math is a crucial idea. They tell you this is a subspace. When they give you a basis for it, it means they are telling you that everything in your subspace is a linear combination of those bases. And they are telling you they are linearly independent at the same time. Okay. Now we studied the null space. Now we're going to learn how to find a basis for the null. So it's easy. It's actually fairly easy. So basis for the null space, and I will elaborate fully by an example. So basis for the null of a matrix. So before that, let me remind you what the null of a matrix A is. So suppose A is a n by n matrix. The null are all the solution, all the x's, such that A times x equal to 0. So the null space is nothing more than the solution of the system Ax equal to 0. Okay. Now we're going to learn how to find a basis for the null. And remember, I showed you twice that the null is a subspace. It means if two vectors solve the homogeneous system, their sum will solve the homogeneous system. If a vector solves it, the homogeneous system, stretching the vector will create another solution. That's really the heart of a subspace. Now we're going to find a basis for it. So question is how to find a basis. And I will elaborate by really an example. Find a basis. All right. So I'm going to take a matrix, A. So I'm going to take A to be the following matrix. Minus 3, 1, 2. 6 minus 2 minus 4. And minus 1, 2, 5. And 1, 3, 8. Okay. So the null are all the solution. It means we have a lot of them. So if I want to find a basis, I first have to know what those solutions are. So find a basis for the null. So first what we have to do is, first, we have to know what are they. So I cannot find a solution for something I don't understand. So first we need to solve. We solve the system Ax equal to 0. So we have to solve it. And we write the solution in parametric vector form. So the first step we're going to do is we're going to solve and write in parametric vector form, something we've done before. Okay, so because I want to find a basis, first I want to understand, okay, what are those vectors that I'm working with? So let us solve. So I'm going to take A, 0. I have to understand those vectors. So, okay, you pick up your calculator. Usually on an exam, I give you the echelon form for those particular problems. And we do it. So I will not do the work. So 1, 0, 0, minus 2, 0, 0, 0, 1, 0, minus 1, 2, 0, and 0, 0, 0. Okay, so if we solve, what was in the first row of A? Minus 3, 6, minus 1, and 1. All right? Okay, very good. So now I'm going to solve. So let us remember, how will this read? Just as a trying to recall everything. The first equation read x1 minus 2x2 minus x4 equal to 0. And the second one read x3 plus 2x4 equal to 0. Okay, and the free variable, so I have leading, I have a leading here. So my free variable are those two, so x2 x4 are going to be a free variable. Okay, and before I move on, I strongly advise you, when you are trying to solve Ax equal to 0, always ask yourself the solution. It means the vector x that we're solving for. How many components does it have? This really helps you to focus. And because A is a 3 by 4, it means the solution here will have to have 4 entries. So we have 4 entries for the solution. It means the solution x, since it has 4 entry, it means a vector in R4. So be very careful where you're working with. Now I have to write this in parametric vector form. So we're going to introduce S and T parameter. So I'm going to put x2 to be S, for example, x4 to be T. And I know that some of you are keeping x2 and x3, which is fine with me as long as you do it correctly. And everything else, it means the leading variables, has to be expressed in terms of the free variable. Because I have the reduced echelon form, it's going to be easy. So x3, if I solve it from here, I'm going to get minus 2t. And x1, I'll solve it from here. It's going to give me 2s plus t. Okay. Now we have to write it in vector form because I am solving A times x equal to 0. So I'm looking at my solution as vectors. So in vector parametric vector form, so we get x equal, so my x, which is a vector in R4, it means it has 4 components. This we're going to write it as S. There is no constant term here because it's homogeneous. It's a 2, it's a 1, it's a 0, it's a 0, plus t times a 1, a 0, minus 2, a 1. Okay, so far everything is something you have seen. So what does this tell me? What does this tell me? Remember, my goal at the end is to tell you how to find a basis for the null. So let's see what does this tells me. It tells me the following. If x is in the null, so if x is in the null, it means if x is a solution of the system, then my x is equal to a certain scalar times the vector 2, 1, 0, 0 plus a scalar 1, 0, minus 2, 1. Where S and T are any variable, can be take any value. Okay, so what is the null now? So my null is what now? Every vector in the null is actually, if you think about it now, it's a linear combination of this vector and that vector. So by writing the null, vectors in the null, using parametric vector form, I can actually start interacting a little bit better with the null. So this is actually tells me, so this shows that the null of A is actually all linear combination. So that's what the null is, all linear combination of the vectors 2, 1, 0, 0, and the vector 1, 0, minus 2, 1. It means every solution of the system x equal to 0 is a combination of those two vectors. So in terms of span, how can I write the null? So the null, if I introduce the language of linear algebra, is nothing more than the span of those two vectors. That's what it is. Okay, so far I'm doing things we've done before. So now, what's the basis for the null? I'm going to skip a line here for a reason. And now, what's the basis for the null? Okay, that's the basis. So let us analyze what we got so far. We found the null, and we realized that but once you wrote in parametric vector form, this tells me that every vector in the null is a linear combination of those two vectors. So the null is nothing more than the span of those two vectors. Everything in it is the span of that. So what is the basis for the null? It means what are those vectors that gives me every other vector in the null? What are the candidates for the basis? What are the candidates? Give it your best shot, and it's going to be correct. What are those vectors whose linear combination give me everything in the null? Let's watch here. Everything in the null is a combination of those two vectors. Everything in the null. Now, moreover, those two vectors are linearly independent. They are linearly independent. We just stare at them. There is no way we can get them as dependent. Actually, most of the time, not most of the time, there is a theorem that once you write the solution in parametric vector form, those vectors will be always linearly independent. So now the null is what for us? Is the span of those two linearly independent vectors. So the basis for the null is going to be nothing more than those two vectors. This is going to be the basis for the null. Okay, absolutely. Because two reasons, their span is in the null, is the null itself, and then they are linearly independent. So the basis for the null is nothing more than those two vectors. And now what is the dimension of the null? The dimension is the number of vectors in a basis. So the dimension of the null is the number of vectors. The dimension is equal to 2. So the null of A, so we write that the null of A is a subspace, that would be too much math, it's a subspace of dimension 2 in R4. It means every vector in the null is in R4. It has 4 entries. Of dimension 2, it means the null is spanned by 2 vectors. So we can some kind of imagine the null to be like a plane in R4. So we can think of it as a plane in R4 in a way. Okay, so let me summarize how we find a basis for the null. It's actually simple. Okay, we have a matrix. If I want to find a basis, we take the matrix for the null. First, I have to know what the null is. So we solve the system AX equal to 0, and we write the solution in parametric vector form. Once we write it in parametric vector form, those 2 vectors we get, those vectors will be actually the basis. Because once I write it in parametric vector form, this is telling me the null is nothing more than the span of those 2 vectors. And those will be always linearly independent. You don't even have to check them. There is a theorem that tells me that. So the basis for the null will consist of this vector and this vector. That's how we find the basis for the null. Now, sometimes we can have 3. We can have 3 free variable. And then in this case, we're going to have the basis will consist of 3 vectors. So how many vectors we have really depend on the basis. Okay, so that's the basis for the null. Let me do one more examples and for the null to basically make sure, because this will be on your exam and usually that's a simple question. That's the way I look at it. So let me take another example. It's actually kind of, suppose I take H to be the following. A little bit make you uncomfortable, but that's okay. All the vectors x1, x2, x3, such that x1 minus 2x2 plus 3x3 equal to 0. So that's my subspace. Okay. Now geometrically, this is a plane through the origin. Geometrically, that's a plane through the origin. All of you who remembered 261, this is nothing more than all the x, y, z, such that x minus 2y plus 3z equal to 0. That's really a plane through the origin. So now my question is, I want to find a basis for h. Find a basis for h by really looking at it as a null space. Find a basis for h. So this is a subspace, which is basically a plane. I want to find a basis for it. Okay, there are two ways to do it. I'm going to do it using the idea of the null. Okay, H is basically the null of a matrix A. But what is A? Who can give me A? What is A? So H are all the solution. Basically, you can think of it as all the solution of this equation. So what is A? So if I want to write this as A times this equal to 0, what's going to be A here? 1 minus 2 and 3. So I can think of that as the null of A, where A is minus 1, 2, 3. Okay, so find a basis for H. I can think of H as nothing more than the null of a matrix, and this matrix is 1 minus 2, 3, so it's nothing more than that. Now let us find a basis for that. Okay, it's really as usual. So we're gonna solve Ax equal to 3. Now I know you are a bit kind of uncomfortable because we've never done one row matrix, but why not? So we're gonna solve that. 1 minus 2, 3, 0. Now there is really nothing here I can reduce. That's my leading. And this will give me the following. x1 minus 2x2 plus 3x3 is 0. x2 is free. x3 is free. So don't, absolutely, that's really what's happening, which makes a lot of sense. If I want to find all the solution of this equation, I can give x2 any value. That's what the idea of a free is. And you give x3 any value, and then I can pick up x1 once I give x2, x3 a value. So x2, x3 can really be take anything, and I can solve for x1, and I get a solution. Okay. So now in parametric vector form, I can write it as, and make this to be S, and this to be T. So this will give me x1 to be 2S minus 3T. x2 is S, and x3 is T. So parametrically, this could be written as S times 2, 1, 0, plus T times minus 3, 0, 1. Okay, so every vector can be written as a linear combination. So it means actually, geometrically, that's the picture. H is this plane. So this geometrically tells me if I take those two vectors, 2, 1, 0, and I take the vector minus 3, 0, 1, this plane is nothing more than the span of those two vectors. So that's really what this is telling me. And I don't know if you guys get into that in 261, that I have no idea if you see anything like that in 261 or not. So X is the linear combination. So it means that the null of A, which is my subspace, is nothing more than the span of those two vectors. And those two vectors are linearly independent. So the basis for my H is 2, 1, 0, minus 3, 0, 1. That's a basis. And the dimension of H, which definitely fit your intuition now. The dimension of H is the number of vectors in the basis. The dimension is equal to 2. And we say that H is a subspace of dimension 2 in R3. So it's not R2, it's a subspace of dimension 2. It means H is a subspace. It lives in R3, but it's spanned by two vectors. Two vectors will give me all of H. So this is called a subspace of dimension 2 in R3. Okay. All right, I of course, stop right there. Last time I stopped 15 minutes early. Don't ask me why. Somehow I read the clock wrong. That's what happened last time. As you guys know, your exam is on Monday. The exam will open at 1:30, as we decided. It will close, I think, at 6. Everything is clear on Brightspace. So no student should have any issue, because it is during class time. And the exam will not take 3 hours. It's not really the idea. It's just to make you feel comfortable. It will be my regular 1 hour, 15 minutes exam. No more, no less. The review is already on Blackboard. Sorry, I meant on Brightspace. It means my old exam is already on Brightspace. And the review is on Brightspace. And I made it very clear that determinant is not covered on my old exam. Determinant will be covered on your exam on Monday. So you make sure to go every question, all the homework for the determinant, okay? And I will put very soon the solution to all the exam. Second, some student asked me to record a review session. I will do that. And my plan is to record it hopefully Friday afternoon. Okay, now what will help me tremendously to make this recording beneficial is that if you have questions about any problem you didn't know how to do, just email me the problem and just email them to me. And then I can look about the questions you have and I can incorporate them into my review, because my review will be basically explaining my old exam and covering 2 or 3 problems from determinant. That's all I have in mind. But if you guys have anything specific you want to ask, do that before Friday. And Friday evening, I will record the review and put it on Brightspace. But it will be very helpful to me if I know what your questions are so I can incorporate them. All right? Any question before I let you go? No, I'm not going to put Kramer's rule on the exam. No, you guys were, Professor Tarforaya told you what it is and explained it, but I will not put it on my exam. All right? Anything else? I'll keep it for the final, I guess. Any other questions? Okay, so please, if you have any questions, email me or come to my office hours. And bye-bye for now. Number 20 from 3.1. What is it about, Chris? I haven't memorized them. You can just speak up. Or email it to me and I will put it on the review. Okay? If you have any questions, just email it and I will incorporate them in my review on Friday. All right? Got it? Grace, yes or no? I want an answer. Okay, I got it. Yeah, email me. Any questions you have, anything, just email them to me. I will put them together and I will address them in my review. I think that's the best way I thought that to help you out. Anything else? Okay, all right, so I'll end the section. Bye-bye, guys.